Okay, so here's another example of curve sketching. And we have this function right here, and we're going to try to sketch this curve. So the first thing it asks us for is the end behavior. Now, remember, when we're trying to do curve sketching, there's just certain things we need to find. We need to find the end behavior asymptote, we need to find the vertical asymptote, intercepts, all of those kinds of things. And we can do them in any order, because in the end, we just use each of them to figure out all of the stuff that we need to figure out. But in this case, it asks us to find in each step, and so we'll just do that in this order, but it doesn't really matter if it just says, like, here's a function, sketch the curve. Like, you can do it in any order. Now remember, an end behavior asymptote, last week we were talking about end behavior of polynomials, but we're not graphing polynomials now, we're graphing rational expressions now. So these are expressions that, see, they have one function on top of another function, so they're different than polynomials, so they don't follow the same rules as a polynomial will. So we're trying to find an asymptote that tells us the end behavior of this polynomial, or of this rational function. In other words, we're trying to figure out, as x gets really huge, what does this function approach? Is it approaching a horizontal asymptote, or is it approaching a slant asymptote? Where's it going? So remember, end behavior asymptotes we find with long division. So I'm going to go ahead and I'm going to divide this, and I'm going to use the box to help me visualize it. So that's x squared minus 6x minus 16. And we know that I'm going to need x cubed when I'm all done. And I'm just going to make that bigger for you. Okay, so I need x cubed when I'm all done, because the answer is x cubed minus 3x squared, and so on and so forth. So that means this has to be x, right? Because that times x squared equals x cubed. And that means that this is going to have to be negative 6x squared. Let's do that in a different color. Okay, negative 6x squared, and that's going to be negative 16x. Okay, and then we know that we need to have negative 3x, right? Because everything inside of this box has to add up to this function on top. Everything inside the box has to add up to that, right? Because when we multiply this factor by this factor, they need to multiply to this. So we're just like going backwards, right? So right now I have negative 6x, and so this is going to have to be positive 3x squared, so that when I add them together, I'll get negative 3x squared. And so what does this have to be up here? This has to be positive 3, so that those would multiply together. So that makes that negative 18x, and that makes that negative 48. Okay. Now my x squareds, my x squared cubes add up. My x squareds add up. Now I'm going to look for my x's. I need negative 25, and I have negative 34. So how many do I need? I need positive 9 x's to balance those out. And then the question is, and this is where a lot of you guys get stuck, is then you're like, well, what do I put up here then to get 9? Well, there is nothing, right? There's nothing that you multiply x squared by to get 9x. And if you look, we have a variable. We have x to the first plus 3, so that's a constant. What comes in polynomials, what comes after the constant? Nothing, right? It's like when you're dividing and you get to the decimal place. It's just the end, right? So now everything after this is just the remainder. So we're going to go ahead and put r right here so that we remember that's the remainder. And so we have 9x, that'll give us our negative 25x. And then we need negative 21. Is that negative 21? Yep, we need negative 21. So we have negative 48. So is that positive 27? Yeah. So in the end, when we divide these two, we get x plus 3 plus 9x plus 27 as a remainder, and so we write a remainder over x squared minus 6x minus 16. And since, what do we care about when we look for end behavior asymptotes? Well, we care about this part of it. We don't care about the remainder. So our end behavior asymptote is y equals x plus 3. So that's a line that we could actually graph as an asymptote. In fact, let's go ahead and graph that right now. Let's come down here and let's graph it. So y equals x plus 3 is a line with a slope of 1 and an intercept of positive 3. So this is our asymptote. That's our asymptote. Okay. Next, we want to look for, it says find the vertical asymptotes and state as each of them is even or odd. Now, so to remember to find vertical asymptotes, we need to factor the whole thing so we can see what's on the bottom. And the problem is this one is, the top is not immediately factorable. We don't just look at it and be like, oh, that's this. It doesn't factor by grouping. So we're going to have to do our rational roots test to find the root of this function. So remember, we take all of the factors of our constant over all of the factors of our leading coefficient. So our possible answers, or our possible roots, are 21, 3, 7, and 1, plus or minus, of course. So we have to take all of those and we have to decide which one is going to be it. Just for time's sake, I think I remember that -1 is the one. So we're going to do that, but just know that you might have to test a few of them to get there. So let's try that out. We're going to go ahead and do synthetic division to see if that is a root. 1 times -1 is -1. That's -4. Times -1 is +4. That's -21, and that's +21. So that's 0. So I remembered correctly. Yay, me. So one of my factors is x plus 1. Because -1 is a root, I can write one of my factors as x plus 1. So what is my other factor? My other factor is x squared minus 4x minus 21, because that's what's left over from my synthetic division. Now, I can factor that some more, x plus 1, and this goes x minus 7, and x plus 3 is going to factor that, okay? And then on the bottom, we're going to factor that as x minus 8 and x plus 2. Those are going to factor. Okay, so here is our factored form. I'm just going to go ahead and erase this so you have a little bit more, it's just cleaner. There you go. This is our factored form. So then we think to ourselves, okay, we're looking for discontinuities, which is where the denominator is equal to 0. So where is this denominator equal to 0? Well, it would be equal to 0 if we put in an 8. It would also be equal to 0 if we put in a -2, because either one of those would make those factors equal to 0. So I have discontinuities at 8 and -2, and then I ask myself, are those asymptotes or wholes? Well, they don't cancel out with the top, which makes them asymptotes. So I have vertical asymptotes at x equals 8 and x equals -2. So I can go down to my function and I can graph my vertical asymptotes at x equals 8, 1, 2, 3, 4, 5, 6, 7, 8, and -2. Okay, and I'm just going to go ahead and extend those up there. You'll see why later. Okay, so we have asymptotes at 8 and -2, and then we check to see if they are even or odd. And now remember, even or odd comes from the multiplicity of the factor that created the asymptote in the first place. So I come back to this factor. This factor created an asymptote at 8. What is the multiplicity of that factor? The multiplicity of that factor is 1. Therefore, this is an odd asymptote. And now I look at this this factor and I say this created an asymptote at -2. And what's the multiplicity of this factor? Well, it's also 1. So that makes this an odd asymptote. So remember, what that means is our asymptote, it's going to approach our asymptote like this, or it's going to approach our asymptote like this. So they're not going to be, both of them aren't going to positive infinity and both of them aren't going to negative infinity. One's going each way. So we just have to, once we get started, you'll see how that actually helps us graph. Okay, the next thing we're going to find are intercepts. Our y-intercept is really easy because we just plug in 0 for x. Remember, our y-intercept is where x equals 0, and our x-intercept is where y equals 0. So we come here, and if we plug in 0 for x, This is super easy. Watch. 0, 0, 0, 0, 0. So when I plug in 0 for x, I get negative 21 over negative 16 because all of these factors go to 0 if I plug in 0 for x. So my y-intercept is negative 21 over negative 16. So we're going to write that. Negative 21 over negative 16, which is actually just positive 21 over 16, which is approximately equal to 1.5. Like it's somewhere in there, right? Because 32/16 is 2. So, all right. Now our x-intercept, we look for when y is equal to 0. And remember, this takes us, we have to go 0 equals x plus 1 times x minus 7 times x, is that plus 2? No, plus 3. Over x minus 8 times x plus 2. Now remember, when we're looking at x-intercepts, the only way for this function to be equal to 0 is if the numerator is equal to 0. The denominator doesn't matter. We could multiply it on both sides and it would just cancel right out, right? So we set each of our factors equal to 0 on the top and find which places this function would be equal to 0. Well, that would be at x equals negative 1, x equals 7, doesn't want to write that, x equals 7, and x equals negative 3. So those are our x-intercepts, and now we have some more things to graph. So we're going to graph at negative 1, 7, and negative 3. So that's negative, negative 1, 7, oh, and it is negative 3, goes right there. And you notice it's on our slant asymptote. That's okay. Slant asymptotes can be touched and crossed. In fact, horizontal asymptotes can as well. Vertical asymptotes are the only ones that can never, ever, 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 ever be crossed. So I know that makes you so frustrated because you're like, I thought asymptotes could never be crossed. But remember, horizontal and slant asymptotes are only talking about as the function gets really huge. So in the middle, when x isn't really huge, sometimes it's going to go across that asymptote. It's just going to approach it as it gets to be really big. Okay, and then last but not least, we're going to graph that y-intercept, which was about 1.5. So here we go. We have everything that we need. We just are looking at this going, okay, now what? Well, here's the thing. We know that for it to be a function, it can't be up here and down here, right? If I had this and this, there would be a problem because it wouldn't pass the vertical line test. So it wouldn't be a function. So that can't happen. So we know that either a piece has to be up here or a piece has to be down here. And the same thing for each of our spots. Do you see we have 6? 1, 2, 3, 4, 5, 6 spots. Either a piece is here or here. Either a piece is here or here, and either a piece is here or here. So we're going to have 3 pieces because our domain restrictions are that x can't equal negative 2 and x can't equal 8, but x can equal all of these numbers, so our function has to exist over there. And our function also has to exist here. And our function also has to exist here because our domain is all reals except negative 2 and 8. So it has to exist in all of these places. So where does it exist? Well, we know it goes through these 3 points here. And so we know, if I can actually get through all these 3 points, we know that it's got to go like this, because it can't get through those 3 points any other way. That's the only way for it to go, right? So then we ask ourselves, okay, what else do we know? Well, we know it has to go through this point, and we know it can't go down because we know this asymptote is an odd asymptote, so it has to be going up, okay? Just because it's an odd asymptote, we know that. And since it's going up, it's going to then approach the horizontal asymptote this way. Now, it could cross, it could be underneath, it could be on top. We don't have the calculus to decide that yet, so it's fine if you have it on top or bottom. Just leave it. So that's that side, that's the middle, and now we need one more spot. We need this one. And so then you're like, well, is it down here or is it up here? Well, think about it. If it was down here, it would be an even asymptote because it'd be approaching that asymptote at the same way. So it can't be down here, it's got to be up here. The other reason it can't be down here is because it can't cross the x-axis again. So it has to be up here. So this is our final function right there with all 3 of its little pieces and the asymptotes.